Guys, what's up? Welcome to anything. And this video we are talking about the DC machines. DC machines, here we are basically we are talking about the type of machines, okay, and the characteristics and also the constructions here. And we will try to solve some questions also. And so let's start. Okay, first of all, a DC mean the direct current, okay, for a machine which have a direct current. Let's, if I talking about the fundamentals, then a DC machine can act either as a generator or as a motor. There is no difference as a DC machine, but the working principle and the input output will be different. Obviously, the generator an EMF is induced in a conductor if it moves through a magnetic field. For a motor, a force is induced in a conductor that has a current going through it and placed in a magnetic field. Now, simplest rotating DC machines. It consists of a single loop of wire rotating about the fixed axis. You can see this is wire, and the rotating part is called rotor, and the stationary part is called as a stator. The magnetic field for the machines is supplied by the magnetic north pole and south pole, and it is very important, got it, that every DC machine have the even number of pole, north south, maybe any maybe 4 5 7 4 4 8, okay, it will be definitely even number. So now with an uniform air gap, very important, it should be in a uniform air gap, uniform around the uniform gap 0.4 centimeter around. I think the reluctance is same under the pole faces. Okay, the reluctance will be same under the pole faces. The voltage induced in a rotating loop. If the rotor is rotate, a voltage will be induced in a wire loop. The voltage on each segment is given by E of IND, induced voltage, and or in any other way they can express it, E of A. Okay, so E of induced equals to V where V cross B dot I. The total induced voltage on the loop size is E equals to 2V IPL. So when the loop rotate thoroughly a 180 degree, segment AB is under the positions pole faces. The directions of the voltage on a segment and its magnitude remain constant. You can see here the graph. Okay, the resulting voltage of E of E TOT, you can see it will be uniform voltage. Now come to the voltage induced in a rotating loop. The induced voltage equations can be expressed in this way. You can see here that 2 of RL B omega 0. Okay, in general the voltage in any real machines will depends on same three factors. One is the flux in the machines, 2 is the speed of rotating, 3 is the constant representing the constructions of the machines. Okay, getting DC voltage out of the rotating loop using a machines called commutator and brass DC machine, DC voltage can be obtained from AC voltage. Very important, what is commutator? Commutator is and brass DC voltage can be obtained from DC voltage. Okay, and you can see here in the image that there is a commutator where this is the commutator and there is a brush. At the instant when the voltage in the loops is 0, the contact short circuit the two segment. Every time the voltage of the loop switches directions, the contact also switch connections. This connection switch process is known as commutator. Okay, so what is commutator? They will may ask the construction switch process. Okay, it is called the commutator. Now come to the induced torque in a rotating loop. The force and the torque on the segment of the loop is given. If F equals to I L cross B, then torque equals to R F sine theta, we know, and this is the commutator, this is the brass, and you can see here the how much torque will be generated here. R is the radius. Okay, the resulting total induced torque in the loop is tau of IND induced is 2 RILB or 2 phi I by pi. Now, induced torque in a rotating loop. In general, the torque in any real machines will depends on three factors: the flux of the in the machines, the current in the machines, the constant representing the construction of the machines. A DC machine constructions. Let's come to the actual point. The DC machine constructions is a very easiest things, and you will understand it very easily if you have any motor in behind or in your hand, then you will understand it more better. So keep any motor like in your car. Okay, toy cars have a motor, so it should keep it in your hands, then it will be better to understand it. And I will also show you the photo here, so you will understand it. You can see here, this is the commutator, this is the commutating point by pole, and this is the pole shoes, and the main pole core is there. This is the brushes, you can see here, this is the brushes, two brushes is there, and the pole is 4 pole is here. Now this is called, the outermost shell is called the York. Okay, and this is the armature winding. Okay, this is the all is a circle is called armature winding, and this is the armature core here, and the rotating shaft is there, so it will be it will be rotating. The compensating winding is there, and shunt field winding, and this is the series field winding, shunt field, series field, and the stator of the DC machines has poles which are excited by either DC current or permanent magnet to the produced magnetic field. In the natural zone, in the middle between the poles, commutating poles are placed on reduced sparking of the commutator. The compensating winding are mounted on the main poles. Those reduce flux weaken commutating problems. Now you can see here, this is the field systems. Okay, very interesting, where the magnetic field will be generating. The poles are mounted on the an iron core that provide the closed magnetic circuit. Very important, it will give you the closed magnetic circuit. And the rotor has a ring shaped laminated iron core with slots. The coils with several towns are placed in the slots. The distance between the two legs of the coil is about 180 degrees. The coils with the several turns are placed in the slots. You can see here, those are the slots, gaps is there. Okay, and now this is the actual constructions of the armature. You can see here, this is the armature core, this is the actual coil, and the coil commutator interconnection is there. There will be the connection here, and insulating between the segment, they are insulating here, and insulations between the segment, commutator copper segment is there, and this is the coil insulator. Okay, and this is the ball bearing, where it will make the more smoother and faster. Now come to the DC machine constructions. DC machine constructions, the rotor coil are connected in series through the commutator segment. So they will make arcs, or okay, you should know the basic things, that rotor coil are connecting in a series through the commutator segment, and the end of the each coil are connected to commutator segment. The commutator consists of insulated copper segment mount on a insulated tube. Two brushes are pressed to the commutator to permit current flow, and they are placed in the natural zone. It is also important that the brass, why we use brass and what it will be, how you will pose it. Okay, it will be pressed to the commutator to permit the current flow. Okay, and why we use the carbon in the sense of brass also important. That is also a matter. We will discuss the purpose of those things, why we use this and that. Mm, but now we are just discussing the what is what. The rotor coil, the rotor are connected in a series through the commutator segment. The end of the each coil are connected to the commutator segment. The commutator consists of an insulated copper segment mount on an insulated tube, which I already talking here. You can see here the actual circuit diagram. If you want to see that, this is the insulator here, this is the north south poles and pole winding is there, this is the shaft, brush and copper segment and rotor winding is there. So now commutator process. The commutator is a process of converting the AC voltage and current in the rotor of a DC machines to DC voltage and circuit at its terminal. Very important. What the commutator work? How commutator work? If the various time they will ask you that commutator, give me the brief discussions of commutator. Okay, the commutations process. The commutations is the process of converting the AC voltage. Okay, we use commutator to make this commutative process, and what it does, voltage and current, AC voltage and current in the rotor of a DC machine to DC voltage and current. Okay, uh, it convert the AC to DC. Basically, the four loop of the machines are laid into the slot in the special manner. The unprimed end of each loops is outmost wire in each slots, while the permitted end of each loop is innermost wire in the slot directly opposites. Uh, Here, the four loops of these machines are laid into the slots. You can see that the four side is there. Okay, coil 1, coil 2, coil 3 and coil 4. The voltage in each of the 1, 2, 3 and 4 ends with the loops of by given E equals to I of B, B of L is I of E and D, I of induced is equals to B plus out of page. The voltage in each of the 1, 2, 3 and 4 ends of the loop is given by I of induced is B plus into page. The total voltage at the brushes is 4E. You can see here the commutator process. It will be time 45 degree, T omega T is there, 45 degree here, and this is that commutator process. The machines at a time omega t equals to 90, the 1, 2, 3 and 4 ends of the loop under the north pole phase. This is the 1, 2, 3, 4 under the south pole phase, and so the 4E will be the terminal voltage here. Problems with commutator in a real machines. Armature reactions. The current through the armature conductor heats up a machine's field surrounding in which has the following effects. One is weakness the main flux, 2 is destroyed the main flux, and 3 is natural path shifts. Problems. What is the problems? L equals to L di by dt voltage occur in the commutator segment being shorted out by the brushes greater than initiative's kick. Those effects cause arching and sparking at the brushes, flashover, reduce brush life and petting of the commutator segment. Brush shift. Okay, the solutions. How we can solve this commutating process problems? Basically, we can do the brush shifting, commutating poles or interpoles, and the compensating windings. Now, solutions to problems with the commutator real life machines. Commutator poles or interpoles, it cancel its voltage in the coils undergoing commutations. interpoles winding are in series with the rotor winding. As the rotor current in induces fluxes produced by the interpoles also increase, okay, producing an opposing effects to that of natural path shift. Now, the solve the problem of flux weakening on natural plant shift, compensating windings are series with the rotor winding, placing the slots curved in the place of the poles the rotor conductor. So we can solve in this way. Now, the internal generated voltage equations of a real machines. The induced voltage in any given machines depends on three factors. Number one is flux. Number two, the three phase, the speeds of the machines of a rotor, and the constant depending on the constructions of the machines, the constant and the speed of omega and the flux. Okay, and you can see here the actual equations. E of A equals to Zp 2 pi RLB by 2 pi A into P into omega. Okay, the voltage out of the real machines, the number of conductor per current path into the voltage of each conductor. You can see that equation. The torque equation of a real machines, the torque equation will be it will be depend on flux, armature current, I of A, and the constant depending. You can see here that the tau of I equals to Zp by 2 pi A, phi Ia equals to K of Ia, phi Ia. The total the torque on the armature of a real machines, the number of conductor Z into the number of each conductor. Power flow and losses in our DC machines, very important. Always remember these things, that there will be some losses will be there in our DC machines. One is because for ideal cases there will be no losses in our machines, but for in the general cases, practical cases, there will be some losses will be here, happen there, definitely happen. So number one is copper losses, because there will be a winding which the where will be the copper, and it was copper, and the brass is made with carbon. It is also rotating across the it is, you know, scratching across the armature. Okay, and so it will be also loss, and they divided, they become loose. Number three is core losses, and number four is mechanical losses and start load losses. So we will talking somewhat about these losses. The copper losses is armature losses and field losses. Armature losses is P of A equals to power, what power loss, I square R A armature current square into armature current resistance, armature resistance, and the field losses is I of F square R of S. For brush losses, V voltage of BD, okay, and into IA. And the core losses, what will be the core losses? The hysteresis losses and eddy current losses occurring in the metal of the motors, very important. The hysteresis loss and the core losses, in exam they will asking about the hysteresis losses and eddy current losses also. Those losses vary as B square, and for the rotor as in the n to the power 1.5. Now power flow, the mechanical losses, what will be the mechanical losses? The frictions losses are losses caused by the frictions of the bearing in the machines. Okay, there will be bearing, and when it will be rotate, there will be some heat will be generated, so mechanical losses definitely will be there. So winding losses are caused by the frictions between the moving parts. Okay, there will be some frictions definitely, so there will be some losses also. So moving parts of the machines and the air inside in the motor causing. Stray losses is unknown losses, you cannot find out it, anyhow it will be losses but some minor quantity by conversions to be 1% of full load. Okay, 1% will be definitely by conversions to be 1% of the full load. Okay, for the full load. And the power flow diagram, here if we're talking about the power flow diagram, then if you power input is there, okay, this is the power input, you put it here, there will be steady losses, there will be mechanical losses, core losses and copper losses, and then you will get the output value. Okay, now power flow diagram for motors, for generator, both are around same, but it will be in the direction, out of the direction. There are four major type of DC generator, namely one is separately excited generator. Basically we are talking about the generator and motor in this session. For generator is separately excited generator, shunt generator, series generator and compound series generator, and compound generator can be cumulative and differential. You can see here, those are the picture here, 1 2 3 4 type of generator is there. Separately excited, it will be separately excited generator. This is the shunt generator, where it will be, there will be a shunt and there will be a series generator. And why it is shunt, there is a shunt, so it will be shunt generator. There is a series, which is a series generator, and shunt series generator. You can see here, this is the shunt series generator. Now the equivalent circuit of a DC generator we are talking. For a DC generator there will be same thing, okay, but the circuit diagram, what will be the circuit diagram? The two circuit are involved in a DC generator. One is the armature circuit and another is the field circuit. For armature circuit you can see here, and this is the field circuit. Now armature circuit represent the Thevenin's equivalent circuits, okay, and it contain an ideal voltage EA and A. Brush voltage drop is represented by the small the field coil which produce the magnetic flux. In inductor L of F and the resistor R of F, and the R of adjust for the field current control. Now magnetizing curve for a DC generator or a performance. The initially generator voltage EA or a DC generator is given by E of A equals to K phi omega. EA is directly proportional to the flux. EA is the armature inductance voltage. The field current is directly proportional to the magnetomotive force, and hence EA brush voltage drop is represented by batteries. Performance of the DC generator are determined by the terminal output permanent IFL and VFT. Voltage regulator also determine its performance. Separately excited generator. We are talking the four type of generator: separately excited generator, series, shunt, and the compound, commutative, and the separately excited DC generator is a generator whose field current is supplied by a separated external DC voltage sources. By Kirchhoff's voltage law, the terminal voltage will be VFT EA minus IA RA. Definitely, since the internal voltage is independent of IA, and the terminal characteristics of a separately excited generator is the straight line. The separately excited generator control of a terminal voltage greater than the methods, two methods. One is change the speed of rotor, and EA equals to K omega phi greater than V of T equals to EA. Change of the field current. The separately excited generator, it is not possible to predict analytical the value of EA to be expand from a given field current. Magnetization curve for the generator must be used in a calculating EA accurately. Net AMF is F of net equals to NF IF minus F of AR, and IFF equivalent field current you can measure by there. The magnetization curve for the generator are drawn for a particular speed of related speeds of the machines. If the machines is turning at the other speeds, then the EA in a machines is related to speed by EA by A of, okay, by n0. Now the shunt generator. The shunt generator is a DC generator that supplies two wound fields current by having its field connected directly across the terminal of the machines. The armature current of a machine supply both the field circuit and the load. IA equals to phi of F plus I of L, and V of T equals to EA by EA minus IARA. You can see the here the actual image and the equations also. The shunt generator voltage build up a shunt generator depends residence residual flux EA equals to K phi omega. Okay, the possible cases for the voltage to fail to build up during starting there may be no residual in magnetic flux. The directions of rotor of the generator may have been revised. The field resistance may be adjusted to a value generated than the circuit resistance. Now the shunt generator. The shunt generator terminal characteristics of a DC shunt generator. The voltage control for a shunt generator DC generator. The change in the shaft speed omega of the generator and change the field resistor of the generator. The terminal characteristics of a shunt generator. Okay, this is the voltage control of a shunt generator. Now the shunt generator is a non-linear analysis of a shunt generator. The key to understand the graphical analysis of a shunt generator is to remember Kirchhoff's voltage law. Okay, this is the key to remember the graphical analysis. The field resistor RF, which is just equal to V of T by I of F and straight line. At no load, V of T equals to E of A, and difference between V of T A is a IARA. The armature current is present in a shunt generator. There is a demagnetizing magnetomotive force and IARA drop. Shunt generator. You can see here this is the example and you have to solve here these questions. Just pause the video and watch these questions and solve it. I just read it for you that 172 kilowatt volt 5 ampere 100 and 1800 tau per minute shunt DC generator is shown in a figure. Okay, and its magnetization curve is shown in figure. So the mechanics is being driven by the prime moves of 800, okay, rotation per minute, and it has following characteristics: RA, RF, and A of adjacent, N of F. What is the no load terminal voltage in this generator? Okay, so how you will find out? Just do it by using the formula before we discuss here. Now this is the resistance 0.5 ohm. Okay, this is the armature. Those series DC the series DC generator generate its generator whose field is connected in series with the armature. It has a few turns to field coil with thick conductor. The terminal characteristics of a DC generator is, you can see here, this is the diversion of the terminal characteristics of a series of a DC generator. Okay, and the cumulative compound DC generator. We are talking about the fourth DC generator. So the third one is the cumulative. Fourth one is the cumulative DC generator, and the cumulative compound DC generator is a DC generator with both series and shunt field will be there, and connected to that the magnetization moving force of the two field are additive. Voltage and current relationships for this generator are, you can see here, and this is the equations basically are series and shunt field coils. The equivalent effects shunt field current for this machine is given by the terminal characteristics of a cumulative compound DC generator is, we are talking about here. This is all about the equations, just read it. The graphical analysis of a cumulative compound DC generator. The following two equations are the key to graphically describing the terminal characteristics of a cumulative compounds of a DC generator. The equivalent shunt field current I of EQ, the total effective shunt field current, and the equivalent current I of EQ represent the horizontal distance to the left or the right of the field resistance in line along the axis of the magnetization curve. And lastly, we just finish video, and you can see here that we are talking about the generator basically here. In our another video we are talking about the motor also. Okay, and here we are learn about the DC machine characteristics and the basically the generator, four type generators, and their equations and some graphs also. So and the last I would like to say that like if you like this video, and comment if you have any doubts regarding these topics, or if we make any mistakes in this video, so please suggest, give us the your suggestions, valuable suggestions, and share it. Obviously share this video on Facebook's, WhatsApps, and your friends who need it, this knowledge, and subscribe to our channel and get latest video on study related every Monday. Click the bell icon to get update notifications. And finally, thanks for watching.